afternoon, everyone. We're back after the lunch break with the second edition of the one6G Summit. I hope you can hear me well. I guess we might have lost someone from the morning, but I hope some other people might be able to join. We have ahead of us a very dense and interesting program. And without any further waste of time, I will give the floor to Josef Eichinger, that is the one6G working group for chair from Huawei, that will chair the next session, which will focus more on 6G testbeds and demo. Please, Josef, the floor is yours.
Thank you very much, Monique. I will now share my screen. Give me a second. Share and start immediately with the presentation. Shared. Good, I'm sharing the screen. I hope you can see my screen. That's the usual question yes. At the beginning of any session. As Monique has introduced, this is a session where we really are a bit proud as a one6G and in particular working group 4 to have 4 different test beds that will be presented today from 4 different partners in one6G. My name is Josef Eichinger. I'm leading this working group 4 since the beginning, since the founding of one6G, and that is really also a challenge, but also a great honor. And I don't want to spend too much time for the introduction, but as you see on the screen, we have 4 different demo sessions here, demo presentations. Demo 1 is about decentralized infrastructure monitoring and declarative programming models. That's presented by Paez from ZettaScale. Then we have a demo about 5G and 6G experimental platform from IMDEA networks, and Joerg Widmer will present this. Then Luciano Mendes from Inatel gives an overview about the platform for the 6G transceivers, very important components. And last but not least, Mohamed Gharba from Huawei Munich will give us a bit let's say an overview about integrated sensing and communication with terahertz and optical wireless. This is all what I would like to start now. I would like to ask you all to send your questions in the chat box or in the Q&A box, whatever you like, because we have 2 minutes, maybe roughly after each of the presentation, to address some questions related to the previous presentations. If you don't understood something or if you are interested to get more, please feel free to send your questions in these 2 boxes here. Yeah, then Ivan, I guess you are ready to take over.
Yes, I'm here. Okay, I'm waiting to share my screen. Okay. By now you should be able to see my screen, my slides.
Yes, I see. Nice
okay, so thank you. Good afternoon, everyone. I'm glad to be here. It's an honor to be here, part of the 6G Summit. My name is Ivan Paez. I'm project manager at ZettaScale Technology. Today, I'm going to introduce you a decentralized infrastructure monitoring application using Eclipse Zeno. So just a brief about the ecosystem. As we have been discussing today, is the 6G ecosystem comes with a heterogeneity of applications that brings a new set of challenges and characteristics. Such applications will need to run in distributed and decentralized infrastructure. At the same time that this infrastructure will generate a large scale of monitoring data. Such telemetry data will be used at the same time to control and optimize the network, and everything will be AI and ML-based automation. However, the problem that exists, as the literature has presented in the last couple of years, is that cloud-centric approach where all the data has to be centralized in a cloud, let's say, that's simply not scale because of some applications have requirements for low latency or data privacy issues or vendor locking. So from our side, we advocate for a more decentralized and distributed management of data, for a paradigm that is really span from the cloud to the edge. Continue. So Eclipse Zeno, which is the technology that we are working on at ZettaScale, is one candidate that can meet those challenges. It unifies data in motion, data at rest, and computations from embedded to the microcontrollers up to the data center. Eclipse Zeno also provides location transparent API for high performance and pops up and queries in heterogeneous systems. It facilitates geo-distributed and integration with third-party technologies, plugins, or backends. So moving forward, the pops-up model is traditional. So we are based in named data networking is part. So we have we can define a key expression for the publisher, and then we can declare some subscribers that will be able to match the given key expression by the publisher. And in the case it's a positive matching, they will be able to receive the data. So we have created a whole key expression languages where we have wildcards. We can have a single wildcard or double wildcard. To play to single wildcard means just one set of chunk of data between two forward slashes, or double wildcard will give you more dynamicity for more than one set of forward slashes, and also empty value. All this will allow you to generate a structure, a hierarchy of resources that can map your topology, required topology. More information can be found in the key expression language, how to use these key expressions. Moving forward, we also support distributed queries. So this is on-demand computation of fresh values, and where this query, they triggers a get, and then there are some resources that has declared queryable with the given selector key expressions, and then exactly similar fashion, if they match, for example, here is where we use the wildcard. For example, this get is interested in the cell average power of all the G-node bits. So he doesn't have to put number 1, number 2, number X. He just put star, and he will get all the cell power data from the machine G-node bits. Sorry. So moving forward, we also support distributed storage. Distributed storages are for on-demand computation of fresh values, and this can be in a distributed way. It continues using the key expression way as a key because it's a data-centric protocol. So this publisher at the left provides a continuous flow of data that will be stored. In this case, an implementation detail, it will be a time series analysis, time series database in InfluxDB. And then at the right hand, we have a querier that queries with a wildcard to get the average power. In this case, he can get historical data using filters. He can even put frames of time, let's say from 1 or 2 days, or from now, the present day, minus 2 minutes or 5 minutes, so get the last 5 minutes of data and things like that. This will be very important to feed later on data analytics or AI ML algorithms that can be deployed at the edge. So going a little bit deeper in the insights of Eclipse Zeno. So Zeno provides support for any topology. We support peer-to-peer in click and mesh topologies. We also support a brokered way kind of communication and a router that moves data from client to peers. Zeno runs also, it has native libraries that are developed in Rust, in Python, or in C. So it can support applications made on these languages and can run also at different layers of the IP stack, starting from the transport, the network, or the data link layer. Zeno has a Zeno Pico implementation, which is developed in C, which can also run on embedded or constrained devices. Next, we have Xeno support multicast scouting based on a gossip protocol. So we define a default IP multicast address and then a UDP scouting port, and then it's able to identify the Xeno entities that are around, and then if they're discovered, they establish a Xeno session to start communicating. Finally, from Xeno, well, it's extensible, as I briefly mentioned before. It supports a different kind of backends, file system backend, in-memory backend, but also storages. InfluxDB, RocksDB, MariaDB is just one of the implementations. And also he has different plugins for other communication protocols like MQTT, DDS, OpenSewa, and we are planning to do another one in Kafka, and there are many others that can be developed. Okay, so that was the introduction of the technology, and now I would like to show you how it works. And you will see some terminal code, so we'll go a little bit down the rabbit hole. I hope you stay with me. So, okay, so the demo I'm going to present was developed in the context of the Daemon. Daemon is an ICT 52 European project that is focused on networking intelligence along the cloud to edge continuum. So the role of our technology was to provide a decentralized data pipeline that will fit the network intelligent algorithms. This pipeline should support very short time scales, so short latency, and also different length of different sizes of payload. So for the different algorithms. Okay, so we have come to the scenario part. Let's imagine. I want you to imagine we are in Paris. We are located in the city of Paris, and then we have two GNOBit stations that are constantly publishing data. They publish the power average sale of each data, and we have here at the left we have a subscriber that is interested in collecting such data. So all this will happen in a PubSub, traditional PubSub fashion way. So this will be seen like this. So this is I will just move to the terminal. We will see. I will stop sharing. I will store my terminal. Okay, so here I'm back sharing. So the first terminal is the first GNOBit station. So we declare a resource, and then we can start publishing data, just like we can declare a frequency, an interval of time. So this one is every half second, and the other one is every second. And here we see how this subscriber here, bottom left, is starting to get the, well, probably should, I'm not sharing the right. Is it yeah, okay. So next on the slides is we need to add a subscriber. So let me just go back to the slides. So now we are interested in deploying a query. Here, the query.
Your slide is not in presentation mode, please. Can you try to change it?
It's not in present.
No, it's not.
Okay, then probably I'm sharing the wrong.
Screen.
Let's stop to.
That's better. Okay,
that's much better. Okay, so as I was mentioning, yeah, this is the first scenario, data in motion just pops up. Now we are adding a little bit complexity. We would like to do a query. So we create a new entity. that will query the last minute of data in this running topology. However, as there is no storage provided, we won't see historical data at the moment. So this I won't have to replicate. It's just it gets empty. So the magic happens that on live system, we can deploy the InfluxDB storage, and then the query will start getting data. This happens in 3 steps to deploy this InfluxDB storage. First, we have to start the InfluxDB, then we start the Xeno daemon with the admin space permissions to add at lifetime. Then we create the InfluxDB, and then we create the storage that matches the key expression that the publishers were deploying data. So in that way, we see that. So I will try to replicate this. This is a live demo with the screens. I will stop share and share my terminals again. There. Okay, here I will trigger an InfluxDB. Then I will trigger a Xeno router, and then I will deploy it in the third window. I will deploy the InfluxDB. So here we can see it loaded the router. It loaded the InfluxDB. I will stop sharing, and then if I trigger again the subscriber, in that way we will be able to see information. Just okay. So in this scenario, I trigger one publisher, I trigger one subscriber, I trigger the subscriber, and then I will trigger the query. We should be able to see last minute of information. So as you see, the advantage of this is dynamic mechanism for deploying queries, for deploying new infrastructure at runtime. So I will go back to my slides and just stop this. Okay, and then I will share. Wait, just 1 second. Okay, now you should be able to see the right screen. So the advantage of this is to be able to have the dynamicity, the capability of distributing all this at runtime without the need to reconfigure the network or to use fixed configuration files. So we can on the fly just deploy one storage that can feed a query that is close to the located to the premises that where we need the information. So in that way, we will have the advantage of the edge and deployment at the edge. So I will give you some handles here. So if you can visit, I try to give an overview of this, and we can have some handles. We are an Eclipse project. We have official repository, and this work has been sponsored by the ICT 52 Daemon European project. And that's it. I'm open for questions.
Yes, thank you very much. I have just a question regarding the number of nodes performance actually, because you said it pops up. How that was a very small scale of for the demo. Is there any limitation with respect in number of nodes because of the performance what you deliver with your solution?
In the number of nodes, no, we have we declare our own routing protocol. So there's no limitation. We have done tests with even thousands of nodes with commercial partners for automotive or for a car, autonomous driving, well, not autonomous guided vehicles, small robots like robot turtles, and we can scale up to hundreds or even thousands of nodes. The advantage is that this protocol is low in overhead, so it requires only 5% of overhead, and the discovery is done in a multicast way. So like TDS requires, I'm sorry to mention some competitor, it also requires a lot of overhead in discovery, and it pushes all the information to other data readers in that case. Yep.
Yeah, as I said, it's a NeurView is the right tool to collect data everywhere, to make data available for AI processing in the different levels of the edge computing. I think this is your proposed method, what you want to demonstrate today.
Exactly.
Thanks a lot.
Thank you.
Yeah.
Thank you, everyone.
Thanks a lot. And we are still working together and working before. And if somebody wants to join, please feel free to check our schedules here. Then after this, I would like to go to the next presentation. This is about the demo tool. It's about NR and 6G experimental system. Joerg, are you ready?
Yes, I'm ready.
Okay. I think you will do it with your own slides.
Correct.
Good.
Okay, should I go ahead and start?
Yes, please start. Yes.
Okay.
In the last presentation, we saw a lot of software. Maybe now we see a lot of hardware. I hope so.
Now it's definitely going to be more hardware, exactly. Okay, excellent. I hope you can see the screen.
Yes, fine.
So then, yeah, let me get started. Basically, at IMDEA Networks, we're a small Spanish research lab in Madrid. I lead the wireless networking research group, and we do a lot of research on wireless networks. 5-6 years back, we were again at the point where sort of it's always hard to build prototypes, right? And every time sort of a new standard comes along, you build a system, like a different prototype to support that standard. And especially now there we were moving from sort of sub-6 gigahertz research to millimeter wave research, which again brings a lot of problems in terms of building good platforms where you can do experimentation. So what we decided to do 5-6 years back is build sort of one platform that is flexible enough to support lots of different standards and lots of different frequencies, right? So we really intend this as a platform both for like wireless local area networking research, as well as 5G and 6G research, and both at millimeter wave frequencies and sub-6 gigahertz frequencies. And the point here was really sort of, then you only need to support one platform, right? That's already complex enough, but at least like you want to try out lots of different things. You don't have like separate platforms for all of those. So of course, that also brings a lot of different requirements in terms of the frequency spectrum, the MIMO order, the bandwidth. So we now have an open source system running based on the Xilinx RF socks, which are relatively quite powerful FPGAs. And to be able to support all this, so we had two main design foci. One is very flexible configuration, right? So that you can actually support lots of different formats, bandwidths, and so on. And at the same time, sort of very high performance, because what we really wanted to do is sort of millimeter wave MIMO research. And then, of course, to support the very high bandwidths that you have at millimeter wave frequencies, the whole system has to be extremely high performance. So in the end, now what we're able to do is sub-6 gigahertz or 28 or 60 gigahertz via different up converters. You see the system at the bottom right with, here it's a sort of mixed configuration with 2 millimeter wave antennas and 4 sub-6 gigahertz antennas, right? So you have a hybrid beamforming system with 2 RF chains for millimeter wave, and you have a normal 4x4 MIMO system at sub-6 gigahertz, driven at the same time with a single baseband from the same RF subboard, right? So that's pretty nice. The standard configurations, of course, are you only use millimeter wave or you only use sub-6 gigahertz, but even these mixed configurations are possible. And we have up to 2 gigahertz of bandwidth per channel and up to 8x8 MIMO at intermediate frequency. Now, for simplicity, the current platform supports a memory-based design, which means it's an offline system. We wanted to experiment with lots of different waveforms, lots of different frame formats, and so on. So every time you want to change something, bring that down to hardware again and actually implement it on the FPGA would be extremely hard. And so for that reason, what we decided early on is that we want very high flexibility in terms of the waveforms. So we want to generate our waveforms, for example, in MATLAB, store them in memory. And fortunately, this system has a lot of DRAM, so you can actually support sufficiently long sort of traces, right? Send them over the air and then sort of decode them again offline, right? So the IQ samples get stored in DRAM at the receiver side, and you basically operate this as a hardware in the loop system. Now, at the same time, some of the functionalities needs to be in real time. For example, the antenna configurations, right? You move a receiver, the link changes, you need to update your beam pattern in real time to maintain your link, right? And so then we have a split where the actual frame encoding and decoding happens offline in software, but most of the rest in terms of channel estimation, packet detection, and so on, like the antenna configuration, happens in real time directly on the FPGA. And we can operate this also in a closed loop system. And for example, especially for the antenna configuration, of course, that's important, right? So you have 2 nodes exchanging data. The receiver node estimates the channel quality and gives feedback to the transmit node to change its antenna configuration in case there was mobility, for example, and you have beamforming millimeter wave antennas. Now, that's the current system that's already available as open source, that's already published. What we're currently working on is a real-time 5G, 6G platform. So for a lot of experiments, such a memory-based approach is the right approach, just because it allows you much, much faster prototyping. You can do your waveforms in MATLAB, you can quickly test different things. Like we played around with OTFS versus OFDM and so on. This, like doing this in hardware would be extremely time consuming. But at the same time, of course, it's not real time. So what we're working on right now is a real-time 5G and future 6G platform. Now, there's of course a lot of prior work in the area. There's Open Air Interface, which is a fantastic platform. There's SRS Run, Aerial from IMDEA, and so on, right? So there are a lot of systems there. Initially, we wanted to just use those and not build our own system, which obviously would have been much easier. The problem is those are a bit limited in terms of scalability. They're fantastic in terms of complexity. Well, or I mean, you shouldn't say fantastic. They're extremely complex because they support a lot, right? They're fantastic in terms of standard compliance. And that's not what we're aiming for. What we're aiming for is the very high bandwidth and very high MIMO orders. And what we found is that all of those existing alternatives, they don't scale very well. They're typically CPU based, or they have some offloading capabilities. But if you really want to run like 4x4 MIMO millimeter wave with 2 gigahertz channels, none of these systems in the medium term future could scale to that performance. And that's why in the end, we decided to sort of build our own platform. And so here we want much less functionality. There's no way we're going to compete with Open Air Interface. We're not going to be standard compatible and so on. But at the same time, we want to move to the sort of very high performance part, especially to be able to be like ready to support future 6G platforms. And so here, what we are currently doing is an FR1, FR2 implementation for 5G and R. on the platform that I've just showed before, and we already have quite a lot of this implemented. It's work in progress. So synchronization signals, carrier frequency offsets, timing information acquisition, channel estimation, and so on is already fully implemented. That already works on the receiver side. And so what we're currently working on for sort of the rest of this year and early next year is to basically have a full 5G and R, FR1 and FR2 receiver, and then the transmitter is going to come later. At the moment, we're still sort of transmitting pre-prepared waveforms, and we're bringing the receiver towards real-time operation. And then, yeah, future extensions would be the real-time transmitter, full support of the initial access procedure, extending into multiple spatial streams. At the moment, this is still a SISO system. And of course, in the medium term, what would be really interesting is an integration with upper layers, where we don't intend to build a MAC, we don't intend to build an RLC. That's just way too complex. And so here, ideally, what we want to use is connect to those platforms like open air interface, like SRS-RAN, use their higher layers, but provide a very high performance lower layer. And of course, there are a few other things, further bandwidth configurations. Now, that's it for the presentation. I now wanted to briefly show a few videos. Unfortunately, the system is sort of so complex that directly live demoing it here would be very difficult. And also, a lot of the stuff happens really sort of, well, in the airwaves and in the memory, and it's very hard to visualize, right? So here, unfortunately, we have to resort to video. And pre-record some of the things. So let me stop the sharing of this, and hopefully I'll be able to go to share. And let me show you a little bit of what we're doing.
Has the video sound, or is it just a video?
The video is without sound. I hope you can see it now.
So, very clear.
Okay, perfect. Yeah. So now let me just briefly talk a little bit to what you see here on the screen. So this is basically one setup with sort of a 4x4 MIMO millimeter wave system. And building this is really simple, especially for this memory in the loop, memory-based approach that I mentioned before. That's pretty straightforward. And all you need is the RFSOC FPGA board. The antennas are from a company called Sivers, but I mean, that's just whichever up converter you want to use here. And then a few cables, connectors, filters, and so on, just to connect everything in a PC host to control the overall experiments, but that's not needed for the actual sort of operation. I mean, that's really just for the control. That's not for anything with the decoding and so on. And as mentioned before, right, we have this on a rack to also be able to do mobile experiments, right? So here you see a student actually moving the system around to see how this works when the channel changes, and especially for millimeter wave experiments, that's very important. Here, unfortunately, again, that's not real time. That's an example constellation that we have for a 4x4 MIMO system with QPSK and an LDPC coder on top of that. But yeah, that's relatively basic. What we can also do is, so the system goes up. What we tried is 256 QAM in this case. And sorry, there's a typo. That's not a 4x4 MIMO system. That's an 8x8 MIMO system. It's sub 6 gigahertz. I think here the bandwidth was 160 megahertz. And again, an LDPC coder on top. You can see the signal isn't super clean, but enough to communicate from what you can see from the constellation diagram. So all of this is working, and the nice thing is it's very easy to experiment, right? So we wanted to test 802.11ax and BE. AX is already out as a standard, BE is not yet out as a standard, and then sort of generating packets for these waveforms and playing around with that in this hardware in the loop manner is actually very simple. Now, in the interest of time, let me skip this. So here, this is what we currently have in terms of the real-time experimentation platform. As I said before, the most common use case is the memory-based design that we use for most of our experiments. But here, this is what currently is already working with the real-time design, right? Sort of transmitting and receiving 40 megahertz sub-6 gigahertz channels or 400 megahertz 5G and RFR2 channels already works. What we don't yet have is the symbol demapping and the LDPC decoder. That's what's currently being implemented. So hopefully within a few months, the full receiver will actually be ready. Here is again an example of the closed loop operation, where we have mobility, we move the system, we move the receiver around, the receiver computes the best beam pattern to use, sends an acknowledgement packet with the best beam pattern to the transmitter, and then the transmitter reconfigures its antenna, and that actually works in real time. And here you can see an example of this, right? So here a student is moving our platform left and right. The transmitter is where the viewpoint of the camera is. We do angle of arrival and angle of departure estimation, formulated as sort of a sparse estimation problem over the patterns you see with all the signal strengths you see with the different beam patterns, right? And so this is what you see on top. It tracks nicely how the receiver is moved to the left and to the right in terms of the angles. And then the beam pattern that is chosen, you see at the bottom, unfortunately, it's not very visible. In very light color, you see all the possible beam patterns. And then in a strong line, you see the received power, which basically just shows that the correct beam pattern is always chosen, the one that actually gives you the highest received power, as you would expect. But that just shows that the feedback loop is actually working. And now finally, to highlight a bit the flexibility of the system, I'll also briefly show some joint communication and sensing experiments. So it is actually possible to also operate the system in a full duplex manner. So for this here, we have the transmit array and receive array active on the same front end, on the same RF front end at the same time, again connected to our to the FPGA platform. And we then do microdoppler extraction and machine learning based activity recognition. And this is just, a student is walking around. Now this is passive localization. So what you see on the top right is the estimated trajectory based on where a multipath reflection is coming from, right? So in the video on the left, you see the access point that's static, stationary. And that's operated sort of in a joint communication and sensing way where we're sending data packets. At the same time, we're looking at how the multipath changes, and that gives us an estimated trajectory. And now from that trajectory, from the specific multipath component of the person, the only one that's mobile in this setting, we actually extract microdoppler. And here what you see is that sort of the microdoppler for this example is very characteristic for the activity of walking. Now, then what we can do with this is, since millimeter wave has so high spatial resolution, we have very directional antennas, we have a very large bandwidth. The nice thing is it can separate the multipath components of a lot of activities carried out by different persons at the same time in the same room. Here in this case, because there's partial occlusion, right? So sometimes one person is behind another person. Actually, what we did is we set up 2 access points that you can see on the left, operated from the same FPGA board. We do activity recognition and tracking for all of these different activities. And actually, sort of you can distinguish all of these activities very reliably. We have an accuracy of over 90% for the activity recognition, even in such very complex cases. So with this, let me conclude. What I just wanted to show is that it is already a very, very flexible platform currently. And with what we're doing right now, it will become even more useful because then, in addition to the offline experiments that we're mostly doing now, you can actually sort of do this online in real time. And in the medium term, we hope over the next year or 1.5 years, it'll be even more useful once you're actually able to connect this to Open RAN software sitting on top to actually connect this to a 5G backhaul and a 5G core. So with this, let me conclude. Thank you very much, and I hope there are some questions. I don't hear anything from anyone. Do you still
Josef,
hear?
I guess
Okay.
we can move to the next person. Josef, are you there? I think maybe Josef.
Hi, Monique. I think I'm the next one. In my case, my name is Luciano Mendes. I'm from Inatel. We do have a demonstration also regarding the infrastructure for transceivers operating for 5G and 6G networks. I think it's very complementary to what Joerg has just presented. I asked Miguel to load the video so you cannot have problems with the bandwidth. So basically, we have prepared a 18 minutes video that shows what Inatel is doing regarding 6G networks. Miguel, could you please play the video?
Welcome to the National Institute of Telecommunications. Inatel was founded in 1965 and, since, has been nationally known for developing and establishing communication technologies in Brazil. And as of today, Inatel is considered one of the main research institutes in telecommunications in Brazil. We offer bachelor's degrees in biomedical, computing, control and automation, electrical and electronics, production, software, and telecommunications engineering. Our graduate program offers both master's and PhD degrees, contributing extensively to research in many important fields. Telecommunications networks and systems, digital TV, Internet of the Future, Internet of Things, antennas and photonics, 5G, biomedical solutions, Industry 4.0, and more recently 6G. Our excellency allowed us to execute many research projects in partnership with multiple national and international institutes. The Radio Communication Reference Center is one of Inatel's research laboratories. Founded in 2015, CRR promotes research related to mobile communications, being one of the pioneer entities to contribute to 5G and 6G studies in Brazil. CRR engaged its efforts to democratize Internet access in Brazil by developing a new radio system for long-range communications. The 5G Range project was born from this initiative, and its prototype provided a solution to connect remote and rural areas using TV white spaces. This allowed Inatel to take part in the first Brazilian 5G transmission. The 5G Range project led to the development of 2 other solutions, which are currently under full-scale production. These are known as LT in a Box and 5G in a Box. Since 2020, CRR is leading the Brazil 6G project, a national-wide research project to develop the next generation of mobile communications. Supported by the Brazilian government, this project has multiple national and international research partners and aims to implement a framework that integrates different 6G elements and applications. We present here some results achieved by our research team.
Hello and welcome to the Brazil 6G demonstration. When 5G network was proposed, it was revolutionary. Several new use cases was presented and they are wishing to fulfill all the requirements all over the world. The reality, however, was a little bit different. 5G new radio has a lot of limitations and you need to bring up with a new network that can actually provide a worldwide coverage and fulfill all the requirements that you have, mainly in Brazil. One emblematic use case for Brazil is the agribusiness one. In this case, you don't need only to have some small amount of data transmit once a day to the applications in the cloud. You actually need a high throughput and reliable network to provide connectivity to drones that deploy chemicals in specific areas in precise agribusiness application. You also need to monitor several animals at the same time, knowing the behavior, knowing what they are doing and where they are living, and acquire this data in real time to feed AI and take actions towards disease and also strange behavior like animals living the area that they are destined to live in. So you have here an entire user case that cannot be fulfilled by 5G networks. So that's why Brazil is investing a lot of time, a lot of research, a lot of efforts to define the requirements for this use case and help to build the 6G networks. We have already provided in work group 1 3 user cases that provide connectivity for machinery, animals, and also for drones. And they are willing to also build a network around it to completely fill all the blocks that's necessary to provide connectivity to those devices. This new architecture that you are proposing for 6G is composed by several layers. The first one is the physical layer, where we are aiming to use new codes, new waveforms, and also exploiting new spectrum. On the core, we are also proposed to using new functions based on network-defined functions and also based on software-defined networks. These functions that we are proposing are mainly based on AI. So AI play an important role in this entire architecture. On the physical layer, AI will be used to control the SNR. Also, it will be used to define if a channel is available or not in the TV white space. And they are willing to use new waveforms, which the PAPR is also controlled by AI algorithm, in order to provide very good throughput and also very good coverage. All those features are being demonstrated nowadays on these transceivers. So we are actually already building the entire physical network using software-defined radio with new waveforms, and the GFDM is the one that you are using nowadays. Also, MIMO is being used in frequencies below 1 GHz to provide diversity and also space multiplexing, improve the throughput for the device. These networks have also been used in Brazil to showcase the situations that we would like to avoid in the future. For example, provide connectivity in schools, provide connectivity in remote areas in order to provide some sort of digital life for those that are living outside the urban areas. All of these architectures is already being built using several players in Brazil. Nowadays, we have more than 10 partners working together to build this network, where you're gonna have the core distributed in several places. You're gonna have also the physical layer distributed among different devices with high capabilities and also small capabilities, but also affordable. And they're also embedded that on different devices such as trucks, drones, and smartphones. So that are all for the 6G networks. Regarding the implementation of the physical layer, you have been used software-defined radio because it's more flexible to evolve, it's easier to implement, and also easier to transfer to the market. With the idea of using open technologies, you are using Gender Radio as a main platform for this development. Most of the functions are running in a single processor, and this processor is taking care of all Mac functions and also all 5 functions. So all the waveforms, coding, everything is implemented to run inside of this processor. So here you have the detailed diagram where you have the block for the MAC layer. In this block, you make all the resource allocation, including controlling the PHY layer in terms of modulation code schemes. We are also using the MAC layer to define which channel we are going to exploit in TV white space. So basically, the MAC layer has all the cognitive functions for the cognitive radio application. On the physical layer, you have all the waveforms implemented in C, and in this case, you are using GFDM, which can be corner cases for OFDM and also single carrier FDM. So we can cover all 3 waveforms with this implementation to have today. The frame multiplexer is very flexible. It can change the number of subcarriers and subsymbols to tackle one specific application. For example, if you need low PPR, we can use only a few subcarriers and a lot of subsymbols. And if you need to have more robust signals against multipass, you can have more subcarriers and less subsymbols, for example. We are also implemented here a digital distortion based on a very strong algorithm regarding of reducing the adjacent channel power. The main idea here is to reduce the influence of this signal in technologies that can coexist, for example, digital TV in TV white spaces. So the idea is not to use RF filter to transmit the signal, and in this case here, you can actually coexist with digital TV. You have done several tests here in Brazil with ISDBT, and you can assure that our system do not interfere on digital TV system. In terms of AI here, the main application is going to be for controlling the modulation code scheme. So in this case here, you also use, besides the information that's received from the device, we also use the amount of error correction that is being done by the decoder for the polar decoder, which is the one implemented here. And in this case specifically, these errors can teach us the exact moment to change from one modulation scheme to another. And this AI algorithm is also running in real time in this SDR that I have implemented. For the interface, for the AI interface, we are now using USRPs, but the idea here is to reduce the cost and go for some very low price SDRs. For example, Blade RF is one candidate, and also XT XR. It's another example that you can use here. All these technologies that we have developed so far has been grouped together in one application, which is the smart farming. So here you can see several equipment that you're using now for this. Here you have the weather station, which collect data from the field and transmit that to the cloud. This weather station is connected to our base station here, and the information goes from here to the internet, where you can see all the information in this dashboard. So this is one example of data transmission from the field to the cloud, where the producers can take advantage of the knowledge of the weather and define, for example, if they're going to apply some kind of chemical in the fields or not. Also here you can have a drone that collects images from the field in real time. So in this case here you have a video drone that can film all the crop and detect areas where you have some stress, for example, lack of water. And this information can also be transmitted in real time for AI algorithms in the cloud that can process this information and then take actions regarding irrigation, and also for deployment of pesticide drones that can control precisely some kind of danger for the crops. So all this information here is going to be available online in real time for the farmers. So this information can help them to increase productivity. So now we can start thinking about improving production without improving the area that is exploited for that activity. So that's a huge change for Brazil.
So I think it shows everything that they're doing nowadays here at Inatel. If you have some questions, I'm going to be here for try to answer them.
I saw a question that was, first, thank you very much for this really impressive video, and also thanks to Valentin that has managed my disconnection time, because suddenly I was dropped out. As I guess it's really urgent to have 6G. Maybe even fiber optic cannot meet the reliability requirements what we want to have. Luciano, I can remember you said that for your special purpose, 5G cannot meet your requirements. Mm-hmm. What in particular had you in mind?
Well, we do have some requirements in terms of coverage, right? So when you go to remote areas, you need to have coverage of up to 50 kilometers, right? So 5 kilometers is not enough for us. We need to cover the entire farm, right? And also make sure that you have enough users under the umbrella of a single base station to make sure that you can afford that base station at location. So improve the coverage is one point. And nowadays, with this technology that you're using, GFDM based on TVOH spacing, we are able to achieve up to 50 kilometers, and you can deliver up to 100 megabits per second to the board of the cell. So it's high throughput, right? Long range links is necessary. Another point is also the cost of spectrum. So nowadays, all the 5G spectrum is basically licensed ones. So you need to go to the auctions, that's very expensive. Operators need to spend a lot of money to buy the license to use the spectrum. And in remote areas, the return of investment is very slow. So you need to provide a cheaper way to use the spectrum. So using TVOH space is a solution that we are pursuing here in Brazil. So those are some of the problems that you have with 5G, that they are not really designed for remote areas. We expect to see some improvements in release 17 and 18, but in my opinion, you need to actually to think about 6G to fully cover all the user cases that you have in remote areas.
Mm-hmm. I mean, mainly also for agriculture, what you have addressed perfectly, where you have maybe even, it's maybe different to Germany, you have big areas, very big areas, but very big farms. Yeah. And is NTN not a solution for you?
I'm sorry, could you say that again?
In this case, is NTN, non-terrestrial network,
yes.
not a solution for you?
Yes, we think that in the future, non-terrestrial network will be part of 6G. So you truly believe that it's going to be fully integrated. You are seeing that happening right now in 5G, right? There's an opening from 2GPP for non-2GPP technology to access the core of the network. So we believe that a non-terrestrial network will be part of 6G. And we truly believe that some applications can go through the satellite, right? Mainly the low orbit satellite. So you actually work with some companies in Brazil. You have here a association of satellite companies which are part of the Brazil 6G project, and they actually are using 6G technology integrated with satellite as a backhaul, for example, and also for direct access. So truly, that's going to be a complementary technology, right? So you need to have the terrestrial one and also satellite to fulfill the requirements of those remote areas applications and rural applications.
Mm-hmm. Okay, thank you very much.
Then
I would like to welcome. Then I would like to go to the next demonstration and demo slot that is presented by Mohamed, and the demo is also about Isaac, addressing terahertz. And Mohamed, are you on stage? Can you start? We cannot hear you.
Thanks, Josef.
I see
Can you hear me now?
Now it's better. Maybe you can go closer to the microphone.
Yeah, super. Yes. So, hello everyone. I'm Mohamed Gharba, a researcher in Huawei. Today we are happy to show you the Huawei use case about the 6G integrated sensing and communications, optical wireless and terahertz for the IIoT. And we have prepared a pre-recorded video for this. Valentin, should you share the video? 6G, the new horizon. Welcome to Huawei 6G Lab. Let's discover together the Huawei latest innovation and know-how. Hello everyone, and welcome to Huawei 6G Isaac experimental use case. I'm Dr. Mohamed Gharba, a principal engineer working on 6G radio technologies for Huawei. 6G is no longer just a platform that connects everything. 6G will go far beyond just communications. 6G will have more capabilities with respect to the 5G, like the sensing and AI. 6G will continue the transformation from connected people and things to the connected intelligence. It will serve as an intelligent platform that offers both integrated sensing and communications called ISAC, and also integrated computing intelligence. The 6G network will serve as a sensing network, and 6G terminals will serve as sensing terminals. This will create new features like sensing-assisted communications. Network sensing enables a new usage scenario beyond communications, which not only improve communications performance and unlock new network service capabilities, but also lay a data foundation for building an intelligent digital world. The Huawei 6G research team is investigating integrated sensing and communications, ISAC optical wireless, and terahertz aspects using different spectrum. Huawei has developed an integrated sensing and communications with a terahertz and optical wireless prototype. In one hand, the 6G ISAC terahertz opens new possibilities for wireless communication systems. The sensing data extracted from the 6G network will not just be used for modeling the physical world. It will also serve as a big data source and entry for AI learning. High data rate communications and high precision sensing are emerging new capabilities for delivering future wireless services. Terahertz is considered an important alternative solution for achieving terabit per second communication rates thanks to the ultra-large communication bandwidth. Furthermore, the seeing beyond eyes concept enabled by ultra-high resolution terahertz imaging can be applied in daily life and production scenarios, including non-invasive health monitoring, checking food safety, finding defects in higher precision manufacturing, monitoring pollution, and supporting machine vision. This concept also means making the invisible visible. Unlike optical cameras, terahertz can penetrate certain obstacles, which achieves high precision imaging and all-weather sensing in invisible conditions with enhanced privacy protection. The unique absorption characteristics of different materials can be characterized by terahertz signals. On the other hand, the 6G ISAC optical wireless extends the frontier of spectrum for wireless communication systems. 6G will extend its reach to optical spectrum in certain home and industrial scenarios. ISAC optical wireless has great potential for high speed, low latency, and low power communication, especially in short-range scenarios. ISAC optical wireless technology can be naturally integrated into existing lighting and light display systems, making every lamp and every screen part of the 6G ISAC optical wireless system. Since the ISAC optical wireless system does not generate electromagnetic interference to the various electromagnetic sensitive devices in operating rooms, it can be safely and friendly used in medical environment. For localization and reconstruction application in the future, high sensing accuracy and resolution are required, whereas for imaging applications, ultra-high sensing resolution is the key. Empowered with the sensing capabilities, the 6G network will be able to provide positioning services for device-based targets and localization services for device-free objects. As such, this will make various applications feasible, spanning from factories to warehouses, hospitals to retail shops, and agricultures to mining. For example, this could enable robots in an automated factory to easily retrieve parts on a warehouse shelf and install them accordingly. Today, we will showcase Huawei 6G prototype of integrated sensing and communication, ISAC. By moving a box with 3D tracking, the box contains a hidden object. We use optical wireless spectrum to localize and control the box movement, and we use terahertz for a non-intrusive 3D imaging, enabling quality control of invisible objects. All sensing data are wirelessly transmitted to the edge using optical wireless for edge computing of sensing data and motion control of all robots. To summarize, we are integrating computing at the edge with the ISAC optical wireless and terahertz.
Hi, my name is Wu, Senior Research Engineer from Huawei. Let me now introduce you to our integrated optical wireless sensing and communication prototype. Firstly, our infrastructure-based optical wireless sensing can replace local sensor on robots in order to not only cut the cost of robot productions, but also provide more robust sensing capabilities. The global controller located in Edge Cloud could utilize this sensing information to perform complex motion planning and multi-robot coordination. This robot can be now sensorless with solely low-level mechanical controller on board. Their high-level robot control logic will be uploaded to the Edge Cloud and transmitted to the robot by Huawei developed optical wireless communication. The Edge controller collects sensing data and communicates with the robots simultaneously using optical wireless, showing our first level integrations of sensing and communications. This implementation presents the feasibilities and great potential value of optical wireless ISAC, asserting its important role in Huawei 6G vision.
Hello everyone, I'm Dr. Han Wen Cao, a principal engineer working on 6G technologies in Huawei. Now I would like to present you our terahertz integrated sensing and communication experimental platforms. The system works at 220 GHz with a real-time signal bandwidth of 2 GHz. With that high bandwidth, we can achieve 10 Gbps data rate wirelessly, as Mohamed just mentioned. What's more interesting is that thanks to the very short wavelengths as well as high bandwidth, it can be used for localize and detect hidden objects precisely. Moreover, as you can see, the system is mounted on a robotic arms. With the mechanical movement, we can create a large virtual synthesized apertures in order to further improve the sensing and localization imaging precisions. The testbed setup can be used to experiment the object detections, sensings, imagings in industrial, logistic, chemical, and medical applications. Now, I would like to start the system and show you how it works.
The Huawei 6G ISAC prototype consists of 3 steps. In the first step, the ISAC with optical wireless is used to track a target cartoon paper box. The box is held by a delivering robot which carries the box to a target location. The optical wireless sensing system is able to detect obstacles on the path and control the robot movement and cooperation with the other robots in the setup. 3D coordinates of the target box and obstacles are transmitted to the robot through optical wireless communication link. The real-time tracking processing is shown by the 3D point clouds. Then a collaborative dual-arm robot will take the box from the robot with the left arm and put it extremely precise right under the other robot arm equipped with a terahertz RF unit. In the second step, the robotic arm uses ISAC at terahertz to scan and image the object in the closed cartoon box, imaging a future and automated quality control checkpoint. There are metal characters placed inside the box, and the 3D imaging results could achieve about 3 mm resolution. In the third step, all sensing data are wirelessly transmitted to the edge, having edge computing and post-processing of the sensing data and high-resolution trajectory data of the antenna movement pattern. Now you saw our current demo with full setup. We would like to show you an outlook of recent progress of next generation of ISAC terahertz prototype. Let's have a look and enjoy what our colleagues in headquarters have prepared.
Let's have a look to our unified ISAC terahertz system. Here we can see the ISAC terahertz system, the transmitter. In another side, it is the terahertz communication receiver. The terahertz transmitter scans the hidden object in the box, and with its sweeping movement, the terahertz transmitter can be directed to the terahertz receiver and communicate to the remote terahertz receiver scan data. This is what we call integrated sensing and communication, ISAC terahertz, and it is in a unified integrated system. A scanning measurement is shown in the screen, where we can see the reconstruction of the scanned hidden object.
To summarize, we have demonstrated our 6G ISAC experiment showing Huawei vision about 6G ISAC. First, the integration of ISAC optical wireless and terahertz with computing at the edge. All sensing data are wirelessly transmitted to the edge, providing edge computing of sensing data and motion control of all robots, benefiting from the high frequency bands and bandwidth. The optical wireless being license-free. It's convenient, in particular for all kinds of sensitive domains like surgery, e-care, and others. Second, the 3D terahertz sensing, the beyond eyes, enabling quality control of invisible objects. 6G device with integrated terahertz eyes that can be used for the daily life, industrial, hospitals, food production, deliveries, shipment, intra and interlogistic. Third, the optical wireless ISAC is enabling the edge-assisted autonomous vehicles and robots. We can reuse the lamps as network sensors and replace onboard sensors. We can also have assisted radio resource and terahertz beam management. It's a complex setup where we have demonstrated an ISAC optical wireless and ISAC terahertz with the edge computing industrial scenario showing Huawei vision about 6G K technologies capabilities. The ISAC concept will not be limited to optical wireless and terahertz bands. Instead, it will be integrated into the full spectrum to meet different sensing range and precision requirements with the aim of providing the most advanced core technologies and solutions for future 6G scenarios. We hope that we could give you an impressive insight of our work in Huawei. For sure, we will meet in future conferences in 2023. I'll give back to the session moderator, and thank you very much.
Yes, thank you very much, Mohamed.
Thank you.
Yeah, very, very interested. Big video covering many topics, actually, a lot of topics. I have also noted some questions from the audience, and one was about the waveform. Which waveform do you use for this ISAC demo? Can you hear me?
I couldn't hear you. Could you please repeat again?
Which waveform did you use for your ISAC demo?
Sorry, I could not hear.
I type it in the chat. Wait a moment. I don't know. Can anybody else not hear me, or?
We can hear you.
You can hear me. That's good.
I can also hear well, Josef.
Yeah. So your question is about the waveform. Sorry, the waveform. So the fully integrated simulations, the fully integrated simultaneous ISAC terahertz is using the communication waveform, the OFDM.
As always, we have used for both for communication and sensing the same waveform. Waveform for both.
Yeah. So the system is the ISAC system is using the communication waveform OFDM for both for sensing and also for the communication.
Another point was if you talk about ISAC, had range tested.
The current simulation for the current system, the ISAC terahertz in the demo is only scheduled with 2 GHz band, but with larger bandwidth and 4x4 MIMO, we can achieve outdoor line of sight up to 240 gigabit per second using the same RF architecture.
That's a 240 gigabit per second. This could be a lot.
Yes.
Yeah. And I'm personally was thinking the terahertz has only a very short coverage, maybe a few meters, but it seems that with a good antenna, but also the video has shown in one of the slides, can reach really impressive distance.
Yes.
Yes, thank you very much. I also hope we can meet us soon, also on other conferences, and also in Working Group 4. And then I don't have any more question on the chat and also in the Q&A. And therefore, I would like to say thanks and take over the screen to continue with my last slide. I hope it's visible. I just want to double check, is my screen visible?
Yes, it is.
Okay, yes. I don't trust anymore this wired connections because I was fading out. Sorry, Joerg, I could not fully follow your presentation until the end, but I'm quite sure we can discuss this later on a bit more offline. And now the sun is exactly shining in my face. Yeah, thank you very much for all of you and for all of the guys in the background, because many of your presentations are based on teamwork. It's not just the presenter, it's there are a lot of people in the background making something happen. And I also want to say thanks for your contribution to the working group 4 in the previous time, and we hope together to do more here within our association. Just some, Joerg, I have one question for you, because I missed your last part. You said easy to set up, it's open source. Is it necessary to build everything by myself or by anybody else, or do you offer also this kind of solutions as a kind of product?
Yeah, so basically we have the bare bones system to just use directly, right? So you can buy the hardware. All of the hardware is directly available, not from us, but from Xilinx and Sivers and so on, right? We have a description of how to put everything together, and then this memory-based system is freely available as open source. Of course, then we've also worked with others to do sort of support as part of a project, or extend the functionality if like an industry partner needs some specific functionality. So we do that as well. But the basic system you can really just set up in your lab, and there we've collaborated with other universities who just set this up to try out some waveform design they wanted to try and so on. So that's something that's like, you're not going to set it up in an afternoon, but it's certainly something that sort of like a good PhD student or an engineer within a few days can actually sort of get up and running with a bit of help from our side.
Without very expensive instruments.
So for what they offer, they're actually not that expensive. So that's also why we chose that platform, right? So the RF socks, they're sort of maybe 10,000–12,000 euros a piece, which is not cheap. But on the other hand, compared to other systems that offer like 8 gigahertz of bandwidth and so on, they're actually very inexpensive, right? So an overall node with the millimeter wave antennas would maybe be then sort of 15,000 to 25,000, depending on if you want like SISO or a 4x4 MIMO node. But again, for sort of millimeter wave software-defined radios with these capabilities, that's actually not that expensive. There are other systems, commercial systems that provide such capabilities, and they cost a factor of 10 more.
Yeah, why I'm asking this is, in the demos right now in all of the 4, we have addressed many things from the higher layers, from, let's look back to the demonstration on ZettaScale from Ivan. He has addressed how to collect data, very many data from many different points of interest. Then we had the experimental system, what you have demonstrated on millimeter wave. We got also more insights into the, let's say, the specific use cases from Brazil and how they solved it. Also this white space and, let's say, taking 6G not just in an isolated band, also maybe in cooperation with or in cooperation with different other existing bands and existing services. And finally, we have also seen 2 times Isaac, one from Joerg and one from Mohamed. And Isaac is still one of the major, let's say, key features, and we need to elaborate more for what we can use it in future and how we can make beneficial commercial benefits out of it. Because we have heard in the morning, it's very important not just to look to the technology, also for what can it be used and what can it be used in a commercial way later on. Saying this, I want to use this time now, the remaining minutes, to give a bit more insight into our working group 4 work. We have also published right now or finalized the guidance for test and validation. That is part of the work item 402. And if you are a member of one6G, you can easily have access to it and download it. There's also a special announcement. What I would like to do right now is that because we have addressed sensing means we we collect data from a terahertz sensor or from an E-band sensor or millimeter wave sensing system, 6G sensing system, and this data could be stored and is stored actually, and could also be offered to other interested parties to take it, to use it for further research on the data. Not everybody is able to build a sensing prototype in order to record this kind of data, even if it is possible, as Joerg said, but maybe not all people are interested to spend this money. And that's the reason why Working Group 4 has now started this initiative to share some measurement data. It's not limited to sensing data, it could be also channel measurement data or something else, even maybe data, specific data recorded during the training of AI systems. So we are here not limited, but I would like to take this time now to say, okay, if you are interested, then become member of one6G, and then we can work together on this database and this shared data. Yeah, that is now, I guess we are a bit ahead of time. Monique, if I'm right, that means I would like to finalize now the demo slot in the session, saying again thanks to the presenters.